We are the We Found the Files team. I'm Kenya.
I'm Audrey. And I'm Corley.
So the core idea of our project is to search through the thousands of publicly available federal documents known as the Epstein files. We built a full end-to-end pipeline that downloads those documents, extracts the text, and then uses CUDA kernels to search, score, and cluster them. Our pipeline has 5 stages. First, data collection, where we scrape documents directly from the DOJ website and court listener. Second, we extract the text extraction from the PDFs. Third, we have CUDA preprocessing, where we build the vocabulary and flatten the corpus. Fourth is the actual usage of CUDA kernels. And then fifth, we have our output and visualization through the Streamlit dashboard. GPU pipeline, we have 3 kernels running in sequence. First is the keyword search in search.cuda. Then we have the TF-IDF vectorization, which turns each document into a float vector. From there, we have the k-means clustering, which groups together by document. And then finally, we have our output, which is the report.html with all the results.
So our first kernel essentially is a search algorithm. So what we're looking at is just a word count. So we essentially tape every document end to end into one vector. So each thread gets a certain index and looks for a word. And then once we have that, it essentially calculates how many times it has that word. And we do that at a smaller scale on our shared memory. So as we see to the right in the example, we have the documents that are our rows and our columns are our words. So for example, if we count Maxwell in document 0 3 times, we essentially feed it to that index. In document 2, same idea. So each one essentially counts that. And then once we have that, we can total the amount. And then once we total the amount, we can essentially send that to global memory. So that global memory would essentially have the word count, and then it would also give us a second parameter that gives us the location of where that word count would be.
So at a deeper level in the GPU, the parallel string search works by each thread handling a single character in a string. The thread compares the current character to the last character in the word that it's searching for. If the character matches, then it continues moving left, so farther into the word, until either a full match occurs or a mismatch occurs. If a mismatch occurs, then the thread exits and it is done. Otherwise, if it keeps continuing and then eventually a full match occurs, then an atomic add happens to a privatized histogram. And then at the end, all of the histograms are added onto global memory. This is not only done for the specific word, so in the full version, it goes for specific patterns that will help with clustering of the documents later. Each thread checks every pattern and then moves to the next pattern if it's not a match instead of exiting after a single word. We also did some speed comparison on this to see how well the GPU acceleration works. The way that we did this was running a Python script and then also the GPU accelerated script. We did this through the Streamlit dashboard. The average speed comparison for a single word lookup was about 1,000 milliseconds on the Python search script and about 2 seconds on the GPU accelerated search script. This was about a 500 times speed up.
For the TF-IDF, so essentially it looks at the previous matrix that we created, and we're essentially assigning a score of importance to that specific word. So for instance, the first equation we have is a log calculation, just in order to essentially, we want to calculate based on the amount of documents we have. So for instance, if we have 50 Maxwells in a 2,000 word document versus a 5,000 word document, we just want to ensure that it properly calculates a score so that we're not basing it on the length of the document. So that score is then calculated on log normalization, and which would be that first equation. And then the second one measures essentially that importance of the word. So for instance, the word the would show up, let's say 100 times within the document, and let's say the document was 150 words. The importance of the word the then is therefore less valuable. So we essentially eliminate that word. It would go down to 0, and that importance then is indexed essentially, or score, if you will. We'll then go to the next step through where we calculate essentially a new vector, which is a directional vector, through parallel reduction, where we calculate the sum of the various scores per document, which we see at the bottom of the example.
So the GPU handles this by first building up a vocabulary of 8,192 terms. It then computes that uniqueness of the word score. The compute TF kernel then assigns one thread per cell in a document by vocabulary matrix. It computes the normalized frequency of each document for each document times term pair. The multiply T IDF kernel runs the same grid again, multiplying each term by the frequency with the IDF weight. And then this prevents words like that from overpowering the document stats, as Corley had mentioned. The normalized kernel assigns one block, which is defined as 256 threads per document, and uses parallel tree reduction to compute the sum of squares across all of the dimensions.
So for cluster dot CUDA, we have our key k-means, which works by dropping bins. Each document goes to whichever bin is closest, and then the bins like scoot to the middle. So then it officially stops when none of the other bins are moving. Essentially, we're doing text normalization first, then using shared memory per block to cache the keyword. List for list for speed. Scoring is based on frequency and positional weighing per document thread. And for picking k, we use k-means plus plus, which with the elbow method to find the optimal numbers of clusters.
So the GPU acceleration works by using the k-means plus plus initialization on the CPU. This is then transferred to the GPU, where the assign kernel assigns one thread per document, computes the similarity against all of the centroids via dot product, and then assigns each document to the nearest cluster. The update centroids kernel then assigns one thread per cluster by vocabulary pair. It adds the sum of all of the document vectors assigned to each cluster, basically computing the average location, so what the document's average is of all of the documents in a cluster. The finalized centroid kernel then divides each sum by its cluster size to get a new centroid position. This is done in a loop until all of the centroids converge on a single point with a maximum of 100 times.
So for our problems that we encountered for the DOJ site puts an age gate. So a plain download just gives you a broken file. So we went around it with a playwright that clicks through the age confirmation before downloading. Our second issue was storage on vendor. We were each allocated a fixed amount of space on the server and we filled it up fast. So we converted each PDF to plain text and deleted the original right after and capped the run at 1,000 PDFs. And then lastly, data races. Our first version of the search kernel gave inconsistent results, different counts on different runs. We tracked it down to sync thread statements that were either missing or in the wrong location. So threads we were reading shared memory before it was like fully written.
For the libraries we used Playwright for the headless browser, Beautiful Soup for HTML parsing, and the Core Listener REST API for docket downloads, PyMU PDF for extraction from native PDFs, and PDF to image to pillow pipeline as our OCR fallback for scan documents. And then the front end is Streamlit dashboard that lets you browse files, run keyword searches, and view documents, and then trigger the full CUDA pipeline.
So the text can run by getting into the the Git repository. Once you're in the Git repository, you'll have to run the scraper. We've run that already because it takes quite a while to run. That downloads the data. So here are all of the PDFs. They were deleted when we converted them to text. The text is going to be right here. And then if you open one of those up, you can see the plain text files are there. To run it, we can just run make. Once it makes, we can run the file, or we can run the interactive script. So I'm going to show the interactive script. Once we're on the browser, we can see how many files were downloaded. So like we mentioned earlier, we had to download 1,000 and cap it at that. It extracted text from 1,000 documents. This is the total number of words, and then this is the total number of sections. So sections is where it was downloaded from. Dataset 1 would be one section. The court records of a specific case would be one section, and so on and so on. It then sorts the documents by word count. So top word counts appear higher. It lists the frequency that they occur. We can then go to the GPU analysis. Here we can set the number of clusters that we want to assign. So say we want 9 or say we want 10. We can then run the GPU analysis. This will create the HTML report, which will then output right here. So here we can see we have 10 clusters. We have the frequency that key terms have been mentioned. So Jeffrey Epstein has been mentioned 2,708 times across 418 documents. You can see other people. And then you can see the locations. So these are different places that are mentioned, common times, legal terms, financial organizations. And then we can see the mentions per document. So if we expand this, we can see all of those. There's going to be a lot of documents here, so I'm going to close that up. We can then see the different document clusters. So cluster 0 would be legal proceedings. Cluster 1 would be personal relations and victims. Cluster 2 would be financial and properties. 3, travel and locations. 4, government and political connections. 5, media, public statements. 6, law enforcement and investigation. 7, unnamed or miscellaneous. And 8, cluster. for specific words. So if we look for, say, Trump, and we can search with the GPU, here this will show everything that goes on in the backend. We scroll all the way to the bottom, we can see the amount of time that each section took to search through. So the GPU string search took 2.1 milliseconds, which is similar to our average. Our GPU TF IDF took 22.9 milliseconds, and the GPU k-means took 265 milliseconds. And that is it.